Okay, today what we're going to talk about is how do we identify the peaks in the spectrum. So I've got a ceramic that's been tested. I've already got the dimensions and the mass and a Poisson's ratio put into the table here. I've measured the flexural resonant frequency and I've the out of plane flexure, and I've got the corresponding Young's modulus of 65 gigapascals. So in this case, we happen to know where this peak is, right, which is the fundamental peak. But sometimes this peak is missing and we only measure the overtones. So what can we do in that case? Well, there's a few things we can do. One thing is, the first thing to do is to try and estimate where we would expect that peak to be. And we do that by clicking on this frequency estimator button here. Now, in this case, we've already got the measure of the Young's modulus, but if we didn't know what it was, let's say we could type in 70 as an approximation. Let's say we think it's about 0.25, well, let's say 0.24. So most ceramics are around about 0.24. If it was a metal, it'd be around about 0.3. So they're good placeholder numbers if you don't know what the Poisson's ratio is. N is the order of vibration, so 1 is the fundamental frequency. And then on this table here, we get the expected outer plane flexure, expected in-plane flexure, expected longitudinal frequency, and expected torsional frequency. We can increase N here. Let's say we want to go up to the 4th order of vibration, which is the 3rd overtone. And then we can use this to identify some of these peaks here, the higher order peaks here. And one way of doing that is to, if you click on this button here, you see that we show lines in the spectrum. So here, this red line is the outer plane flexure and it matches this one. So this red line here is at 3,253 or thereabouts. Now let's see if we can identify some of these overtones. So let's go to the 2nd order of vibration or the 1st overtone. Click here. You see the red line has now moved to this other peak. So now we can identify the flexural frequency for the 2nd order of vibration is this peak. This is the flexural frequency for the 3rd order of vibration. And this is the flexural frequency for the 4th order of vibration. These peaks here, those peaks are the overtones. This peak here is the fundamental flexural frequency. Now, one thing to notice, we measure this at 10 Hertz. That's the resolution. It means that the waveform is measured for a relatively short period of time. Now, if you look at the spectrum now, you see that the fundamental frequency is this one, vibrates for a long period of time because it is the lowest frequency and it decays much more slowly than the higher frequency overtones. So you'll see that the overtones pretty much peter out by about here, whereas the fundamental frequency vibrates for much longer. That's the fundamental frequency vibrates for much longer. So one thing we can do, if we want to try and just get this one peak, is to offset this waveform here. So as I move this, you should see these peaks going down. So we pretty much eliminated the overtones by offsetting the time, or the waveform, by offsetting the waveform by 50 milliseconds we've eliminated the overtones and we just get the one peak. So that's one method we can use. Another method would be, since we know that the fundamental flexural frequency is around about 3000 Hertz, we can zoom in this graph around that peak. So now we've eliminated the overtones and we will just get the peak here. So we can do it that way too. Perhaps the simplest method though, let's look at this one. If you look carefully, if I go to testing info, you see that I measured this with the xylophone mallet, the ME101 xylophone mallet. Now, by using a xylophone mallet, the resonant frequencies or the energy imparted into the sample is reduced to the lower frequencies. So the sample is going to vibrate at the lower frequencies because most of the energy is in the low frequency part of the spectrum. That means that we eliminate all the overtones by using this xylophone mallet rather than the standard impulse tool. And if you look at the spectrum now, you see basically we've only really got one line here. The others are pretty much diminished. The overtones are fairly weak. We've got a very strong fundamental frequency. And because I used the xylophone mallet, I actually increased the resolution. And I used a resolution of 1 Hertz, which increases the time here. That increases the time. All right, so anyway, that's how you can just get one peak at the fundamental frequency using a xylophone mallet. That's one method. The other one is to offset the waveform using the standard impulse tool. And yet another method is to use the standard impulse tool and just zoom in around the expected frequency range. And you calculate the expected frequency range by using this frequency calculator. Now let's move on to the actual sample that you're interested in. This, if we go to the frequency estimator, we type in the expected Young's modulus. We type in the expected Poisson's ratio, and we go up to the 4th order of vibration. Now we see what the expected frequencies are. We see the expected frequency for the fundamental is about 1800, 5000 for the second order of vibration, almost 10,000 for the third order, and over 15,000 for the fourth order. Now I believe you measured this one by mistake, because if you use this frequency and place it here, you end up with a Young's modulus of about 3000 gigapascals. And we know the Young's modulus should be 110. So the correct frequency should be around about 1800 Hertz.